Now, if we put the last two sections together, it gives us a way to start to think about how to classify problems according to their difficulty. Let's look at how that works. So what we're always looking for is a problem where the algorithm matches the lower bound. And so one way to do that is just use reduction. So in order to, want to prove that two problems, x and y, have the same complexity or the same resource requirements, first we show that x linear time reduces to y, and then we show that y linear time reduces to x. And with that way, even if we don't know what the complexity is at all, we know that x and y have the same computational requirements. And this is what we just did for sorting in convex hull. In this case, we know that both of them take time proportional to n log n, but the reducing one to the other in both directions shows us they're equivalent with respect to computational requirements. In the one case, reducing sorting to convex hull gave us a lower bound. In the other case, reducing convex hull to sorting gave us a useful algorithm. But together they're useful because it helps classify those problems. Now there is a bit of a caveat to this, and this is a little bit of an idealized situation, but it actually is something that can lead to trouble in the real world. So we have these two problems, and we have these two propositions that they linear time reduce to one another. Now it could be that in a big software engineering effort, there's a lot of people making decisions, so we found out they have the same complexity, but maybe some system designer has a big project and there's a lot of things, so they need both sort and convex hull. And one programmer is charged with the job of implementing sort, and understands that, wow, could do that using convex hull. I learned this cool trick. And the other one knows the gram scan and says, okay, I'm going to index a convex hull using sort. And that's in a big system, and that's going to lead to a problem. It's an infinite reduction loop, which certainly is going to lead to problems. Whose fault? Well, that would be the boss. Alice and Bob just did what they were supposed to. And it's, well, somebody could argue Alice maybe could have used a library routine for the sort, but you get the point. For a more complex situation, this definitely could come up. Just to show the power of this kind of technique and how it relates to research that's still ongoing in computer science, let's look at some simple examples from arithmetic. So here's the grade school integer multiplication. Let's do it with bits. So I have two n-bit integers. I want to compute the product. And this is the way you learn to do it in grade school. For every bit in the bottom, you multiply it by the top, and then you add them all together. And that's going to take time proportional to n squared. You have n bits, and you have n rows, and so that's time proportional to n squared. But now nowadays people are doing integer multiplication on huge integers because mathematical properties of integers play an important role in cryptography and other applications. So people are interested in algorithms that are faster than quadratic for something like integer multiplication. Now one thing that you can do, first you can do with reduction is people have figured out that you can take integer division or square root and all different other integer operations and reduce them to integer multiplication. So you can show that all of these, and vice versa, and so you can show that all of these things have the same complexity, even though we don't know what it is, just by simple reductions one to the other. And you could imagine how to do divide to multiply and so forth. These have been done in all different directions. So now the question is, so now they're all the same difficulty as the brute force algorithm. How hard is the brute force algorithm? Well, people have studied that for a long time. And actually, one of the earliest divide and conquer algorithm by Karatsuba and Hoffman showed that the integer multiplication could be done in time n to the 1.585. And it was divide and conquer. We divide the integers in halves and find a clever way to combine it to reduce the exponent. And people have been working on this. You can see through the decades, actually, there's a big breakthrough just in 2007 that is getting it much closer to n log n, although there's no known lower bound for this problem. Could be linear. So people are still going to work on it. So in all these different algorithms, they get more complicated, maybe useful for very large n or for different ranges of n. And actually, in practice, there's the multi-precision library that's used in many symbolic mathematics packages has one of 5 different algorithms that it uses for integer multiplication depending on the size of the operands. And again, in applications such as cryptography, the n can be truly huge, and people want to do this computation. We don't know what the difficulty of integer multiplication is. We just know that all the integer operations are described by this one thing. And it's similar for matrix multiplication, another famous problem that people are still trying to understand. And again, the secondary school algorithm to compute the entry in row I and column J, you compute the dot product of the ith row of one argument and the jth column of the other. And the dot product of that fills that entry. You do that for every entry. So that's going to be time proportional to n cubed because you have to do n multiplications for each of the n squared entries in the result matrix. And again, there's all different kinds of matrix operations that can be proven to be equivalent in difficulty to matrix multiplication through reduction. And so that's however difficult matrix multiplication is, all these other things like solving systems of linear equations and determinant and other things. But how difficult is it to multiply 2 matrices? So again, reduction gives us a big class of problems to make it even more interesting to know the difficulty of this one problem, and then research on the difficulty of this one problem has been ongoing. In this case, running time is n cubed for the brute force algorithm, and who knows when that was discovered, I don't know, 18th century or 15th or something. But once computers got involved, Strawson's famous divide and conquer algorithm, like Karatsuba's for integer multiplication, breaks it down through divide and conquer and gets the exponent down to 2.808. And people have been working through the years to find successive improvements to this. The last one went from 2.3737 to 2.3727, which doesn't seem like much, but maybe one of these research results will be a breakthrough that will give us an efficient new algorithm for all of these problems involving matrices. So again, it's very useful to have classified all these problems and make even increase the leverage of the research even more. So when we started this lecture, we started with the idea that it'd be good to classify problems, but it's tough to actually classify them because there's new research involved, even for things as simple as integer or matrix multiplication. But at least what we can do is put the define complexity classes. Even though we don't know what it is, we know there's a lot of important problems that have that same complexity. And there's a really important one that we're going to talk about in the last lecture called the NP-complete problems, and all kinds of important problems that fall into that. But as the time wears on, researchers have found ways to put many, many problems into equivalence classes. So at least we know that those problems are the same difficulty, even if we don't know what it is. This is actually called the complexity zoo. There's really a large number of complexity classes. Now, a lot of these are definitely theoretical devices that are only important in filling in or understanding of some important part of the theory. But many of them, like matrix multiplication, integer multiplication, are very important to practical algorithms. So there's certainly a huge amount of research still going on into trying to understand computational difficulty of problems. So in summary, we use reductions to design algorithms, to establish lower bounds, and to help us classify problems. But in practice, we've been using them already. We designed algorithms that made use of priority queues in effective ways. That's a reduction, and lots of algorithms for sorting. And really, that's the idea of reusable software modules. We find fundamental problems, and we develop implementations that can be used by clients. Every client using an implementation is doing a reduction. And the other thing is that reductions help us determine the difficulty of our problem and guide our search towards finding an efficient solution for it. So in particular, when we get to extremely difficult problems, we'll know whether or not we should look for an exact algorithm, or we should find something that doesn't quite solve the problem. And we'll talk a lot more about that in the last lecture. But in all of these studies in the complexity zoo and in any algorithm that we're going to develop for a complicated problem, what we're going to want is reduction to link the new problem to problems that we know how to solve.